fields and particles. So basically, we've seen things like the action for a point particle. Now, this action for a point particle represents a particle of mass m. On the other hand, you have a quantum field theory for particles of mass n, scalar field theory. We want to understand that connection between those two concepts. So that's where we're getting today. We'll begin with light cone fields. So let's do scalar field first. Now, for a scalar field, we have a field equation that you've seen many times. It's d squared minus m squared on the field phi of x is equal to 0. We're going to use Fourier transforms to do most of our work. So here we'll write phi of x equals integral over some number of dimensions of the momenta times e to the I p dot x times phi of p. And most people would maybe use phi tilde here or something, but if we keep the arguments, we can know that as a function, this function of x is not the same function of p, but just rather than putting all these tildes, we leave it like that. This object is in general complex, and the reality condition, phi real, implies that phi of p star, the complex conjugate of phi of p, is equal to phi of minus p. That's something you prove with the definition of the Fourier transform. So the condition that this is real implies something for phi. Now, if we have Fourier transform here, any partial derivative, when you have the Fourier transform, brings down a factor of IP. So when you try to figure out what this equation looks in momentum space, you get minus p squared from d squared. And the minus m squared, you get p squared plus m squared on phi of p is equal to 0. It's an algebraic equation because p is now just a number. And this is almost too trivial of an equation, but nevertheless, that's what it is. This actually says that if you choose a momenta p such that p squared plus m squared is different from 0, then phi of p is 0, because the product must be 0. There's no way to avoid this. So if p squared plus m squared is equal to different from 0, phi of p is 0. And if p squared plus m squared is equal to 0, then phi of p is arbitrary. Kind of strange looking, but that's correct. That's what it is. So what is p squared plus m squared? P squared plus m squared is equal to minus the energy squared. We're putting the speed of light equal to 0, plus p vector squared plus m squared equal to 0. So that's when this holds, the energy is square root of p squared plus m squared, and that's what we'll call the energy EP, the energy of the particle. This particle has those energies if it has momentum p squared plus m squared. Nevertheless, the scalar field mathematically is described by this whole thing. So we can imagine momentum space. Here is P1, here is P2, here is the energy. And this surface minus E squared plus P squared plus M squared is a hyperboloid with two sheets. So if you fix some spatial momenta, you get some number here, and you take the energies are plus minus EP. So for some spatial momenta that you fix on this horizontal plane, you get an energy and a minus EP, two solutions. So this surface is here. So the solution of the equation of motion of the scalar says that the scalar is 0 everywhere else in the world. But if you happen to be on the surface, it takes some value that is arbitrary. You would expect, even though it's arbitrary, that on the surface is basically continuous or has some derivatives or things like that. But it just lives on the surface, on this hyperboloid. Moreover, if you have a point that has some values of E, EP, and P, there is the antipodal point that has values of minus EP and P, and minus P. Totally antipodal point. And if you know phi here, you know phi at the antipodal point because of the reality condition. Phi and the antipodal point is the complex conjugate of this. So as it turns out, it's sufficient to give the values of the scalar field, say, on the top, and then you know the values of the scalar field at the bottom. Another way of saying it is that phi of P, if you have some fixed P, is two real numbers and fixes the value of the scalar at 2 points. 2 points. P and minus P. So basically, we have one real degree of freedom per point, because you need 2 degrees of freedom to know phi of P here, but it serves for 2 points. So two reals for 2 points, we say 1 real for 1 point, and we call that 1 degree of freedom. So the scalar field, in this sense, has 1 degree of freedom, DOF. Okay, so what else do you know about the scalar field? This is supposed to be things that, should be fairly familiar to some degree. Well, there's a quantum field. There's the quantum field. Is the field operator. Phi of t and x is an operator. And people, will write something that makes sense. You sum over spatial momenta, 1 over 2 EP. EP is the energy here. And then you put annihilation operators labeled by the spatial momenta, e to the minus I, EP, t plus I, p dot x. And I'll continue the second term here, plus AP dagger, e to the I, EPT minus IPX. Field operators, you've been seeing that many times already. There's creation and destruction operators. The interesting thing is that they are labeled by the spatial momenta. And here is the energy associated to that spatial momenta. And that's it. And this is how you solve the problem of negative energy states in the quantum field theory. The particle of momentum p has energy EP and not energy minus EP over here. And this particle is its same antiparticle. It's a real scalar field. And you have this creation and destruction operators. We call this a field operator because the field is an operator. X is not an operator anymore. X is a nice, simple variable. Now, this creation and annihilation operators satisfy AP, AK. If you've put this on a box so that this is discrete, the momenta, we just say delta PK, A dagger, I'm sorry here. And what are your particle states? Particle states, well, we define a vacuum, which is translational invariant, and then we create particle states by acting with this operator. So an AP dagger on the vacuum is a particle of momentum P. Particle of one particle, momentum P. If you have AP1 dagger, AP2 dagger, up to APN dagger on the vacuum, that's a multi-particle state. Particle. Cool. And if it's n particles with momenta P1, P2, up to Pn. So the scalar field can create all these particles, and that's all nice. Now, we used to have in quantum mechanics the momentum operator. That was P equal h bar over I ddx. What is the momentum operator in a field theory? Well, in a field theory, the momentum operator should tell you that this state, for example, has momentum P. So momentum operators, all operators are created with creation, are written, not created. They're written with creation and annihilation operators. So for example, if you want to write the momentum operator, P, it would be written as the sum over all possible values of momenta, of those values of momenta, times AP dagger times AP. Some kind of number operator like that. And you can realize that this is true. If you act with this on this state, the A with the A dagger, maybe I should call it K so that it's a little less confusing. K, K, and K. If you act with this sum over this thing, you pick up a Kronecker delta of K and P, then you get the same A dagger acting on this, or the same state, and it will be an eigenstate with momentum P. So this operator still exists and makes sense. In the light-cone gauge, which is where we're heading to, we change one little thing. Here, all the labeling is done with the spatial momenta, and the energy associated to that spatial momentum is fixed by the on-shell condition. That's how you write your field. If you would be doing this in the light cone, you have momenta P plus, P minus, and P transverse. Well, the energy is this one. This is the energy, P minus. And therefore, the labeling of the states that here is done with the spatial momenta, the spatial components are P plus and P transpose. So in the light cone, you sum over P plus and P transpose and put here P minus, whatever it is, and you have oscillators that are labeled by P plus and P transpose. So here you have oscillators, A dagger P plus, comma, P transpose. Each oscillator is like this, A dagger, for example, labeled by those things. And if this is the vacuum, This is the one particle state. And you could put several of these with a P1 plus, P1 transverse, all these things like that. So that's it. That's a scalar field. Lots of things. This is the kind of thing that in quantum field theory you talk for a week, probably. But now, in a way, I was just setting up notation for you to appreciate what's going on and be able to do more things. Questions? Yes, June.
Yeah, can you clarify or explain why P minus energy is associated with only P minus and not P plus and minus?
Yeah, we decided that we would call x plus time and x minus space. And then we said the pairing in IPX always pairs the momentum with the corresponding coordinate. So this pairing here would be e to the minus p minus x plus minus I p plus x minus. So p plus is associated with space, and p minus is associated with time. That's why this is the energy, and we can think of p plus as a spatial component of the momentum. So P minus is energy, P plus is spatial momentum in light. Sounds sort of funny, but things are a little reversed, and should maybe go back to first couple of lectures when we talked about that. Other questions? I'm mostly worried if the notation here is unclear, because, a question like, I don't understand what this symbol means is very appropriate if anything is unclear here, because we're going to use this notation. So, anything? Yeah.
Just one question. So, when we've seen field theory before,
Loud.
okay. So AP in field theory, that P is usually a 3-vector momentum.
3-vector.
Right? So now you label it a 4-vector, or rather, components of 4 vectors, including P plus.
No, it's not a component of 4-vector. If you have a P transpose, free transverse is P2 and P3. So there are 2 components here. Between this one is 3 again.
Yeah, but your P plus and P minus contains, what do you call that, components of P0.
Forget about P0 now. The energy in the light cone is P minus, and P plus is space. So you use, in that coordinate system, the light cone coordinate system, light cone frame, you should think of this as spatial, 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 time. And don't go back to the idea that, well, it's a mix. It's almost like saying now, complaining that, oh, but x plus is not really time because it's an equal amount of this and that. You just have to take it as time now and treat it as time. And so we have to treat P plus as spatial. Yes?
You might have full expression for the quantum field in the phi.
I probably, it probably is this one. You would write 1 over square root of V sum over P plus P transverse, 1 over square root of 2 P minus, and then A P plus P transverse, exactly the same thing.
Let's say the index and the exponential there.
Yeah, it will be e to the, just follow it the same thing. This index in the exponential, the first one is e to the IPX, and the other one in the other exponential is e to the minus IPX. So put what the light cone thing is. Expand the way we wrote it before, and just take it.
The P minus always positive.
P minus is always positive. There's never a problem with P minus because you have minus 2P plus P minus plus P squared, P transverse squared plus M squared is equal to 0. So P minus is always positive.
Positive. But here you include P plus and P minus.
Yeah.
So in order to show it.
Yeah. Oh. That's right. So 1 second. That's a good question. We should. You're probably right here. Very good question. So P minus is 1 over 2P plus, P transverse squared plus M squared. So this P minus in here can have either sign. So that's a good question. There's two possibilities that I should verify. It's a good question. Okay, there's two possible things that could be happening here. When we'll write the Hamiltonian for the particle, this problem will disappear. This P plus will go away. And that's probably the deeper reason. You will see it in a couple of minutes when we'll do the Hamiltonian. So this P minus, at this moment, I probably leave it like that, although I feel a little uncomfortable indeed. So maybe I'll try to get back to you guys on precisely what you're supposed to do here. On the other hand, we'll see in a second that the Hamiltonian doesn't have the P plus here. And that's probably the key factor that makes that there's no problem, that the energies are always the right energies. So there's a small possibility that I have to just sum over positive P pluses here, but I feel uncomfortable saying that. So I'll check it. So let's do now photon states. So what is the equation of motion for a Maxwell field? It's this one. dA mu minus d mu del dot A equals 0. And what is the gauge invariance? Delta A mu equals P mu epsilon. I don't know. I'm going to still write the derivative, d mu epsilon. That leaves this equation of motion invariant. Now, if you go to Fourier space, so you introduce A of P, you Fourier transform. Here you have two derivatives. So the i's times the signs have the same effect on both terms. You are differentiating the Fourier transform. So this becomes P squared A mu minus P mu P dot A equals 0. And this actually becomes delta A mu of P equals I P mu epsilon, because a partial derivative brings down an IP. And this is an invariance of this equation. So what is the idea of the light cone gauge here? Well, you have A mu's that are of the form take values A plus, A minus, and AI. Now, we've done classical light cone already for the string. So what did we do there? We put a very simple form for X plus. We assume we had the X transverse, and we solve for X minus. So it's going to be very similar here. We're going to try to, I can put this like delta A plus of P equals I P plus epsilon. That's a gauge transformation of A plus from here. And since epsilon is arbitrary, you could choose anything to gauge away A plus. you can say, let me have epsilon equals minus A plus over IP. If you put delta A plus equal to this, well, epsilon is going to be minus the field over IP. You substitute here is minus the field. You can put this to 0. So can set A plus equals 0. So basically, the intuition is really simple here. This P plus is like a number here. And therefore, for any value of P, epsilon is arbitrary, so you can just use it to set this to 0. A plus becomes 0. Now, if A plus is 0, what happens? This is called the Lightcon-Gauge condition. Lightcon-Gauge. So, well, you go back to your equation of motion and try to learn what happens. Take mu equal plus. Well, if mu is equal to plus, this term is 0, and you get minus P plus P dot A equal to 0. So P dot A must be 0. And what is P dot A? Well, P dot A is minus P plus A minus P minus A plus P I A I. That's P dot A. But this term is 0 because A plus is 0. So from here, we can solve that A minus is equal to 1 over P plus of Pi Ai. Now, in Lightcon, you always assume that P plus is different from 0. Different from 0. This is an assumption. It doesn't hold all the time in all cases and in all circumstances. It may not happen always. So in a sense, there's a little singularity associated with ideas in the Lightcon, and certain electromagnetic fields, very peculiar ones, photons that have exactly P plus equals 0, would not be tractable this way. But it's a set of measure 0. And generally, people don't worry. There are physical applications, however, in which Lightcon-Gauge is not good enough for doing the problem. So with this caveat in mind, we have solved for A minus in terms of the AIs. So at this moment, we go back to the equation of motion again. We have PA equals 0. So the whole EOM has become P squared A mu equals 0, which says that P squared A plus is equal to 0, which we knew because A plus is equal to 0, that P squared AI of P is equal to 0. That's interesting. These are massless degrees of freedom. Remember, the scalar was P squared plus M squared phi of P equals 0. That was a scalar field. If you don't have an M here, it's a massless scalar degree of freedom. So this is like having D minus 2 massless degrees of freedom, as if you had D minus 2 scalars. They're not really scalars in the sense of Lorentz transformations, because they carry an index. They transform under rotations. But they behave as the equation of a scalar. Therefore, in terms of degrees of freedom, each value of I is 1 degree of freedom. And there's D dimensions. You lose 2 from here, and then you have D minus 2 massless degrees of freedom. The last component of this equation is P squared on A minus equals 0. And that's true because if p squared on ai is equal to 0, p squared on a minus, you put the p squared, and you go up to here, the p squared times ai is 0, so this equation is also true because of the way we solve for a minus. So, photon states. How would you have photon states now? Well, just like you expand the scalar field and you have oscillators for the scalar field that used to be of the form A of P plus P transverse, like that. You now have oscillators that have an I in here because each component of the gauge field behaves like a scalar field. So each one will have its own oscillator. Or if you have a mode expansion, you're trying to write AI, the full field, quantum field AI, and you will write it with some sum of momenta, and your oscillators have to have the I in there. So you have all these oscillators acting on the vacuum, and these are one photon state. More generally, you can combine them, so you can sum several of them. In quantum mechanics, a single photon state can have many polarizations. Is that right? Can be in classical mechanics, we say, okay, one photon would have to be one way. It's polarized this way or this way, but just like a spin can be up and down at the same time, photon states can be in several states of polarization at the same time. So you can sum them up, psi I, AI, I'm sorry, there's a dagger missing here, P plus, P transverse on the vacuum, and you sum over I here. So numbers times the different states. This is a one photon state as well, a general one photon state. Then we do gravity. What's different about gravity from the photons? Well, if you have gravity, you have a field. So I'm going to sketch only the results because it takes a little bit of time, and the details are really not all that complicated. You have a field H mu nu. What is this field? This is the field that comes when you have the metric and you expand it as flat space plus a little fluctuation. And this fluctuating field is the one we analyze, the field associated to a spin 2 field. Or we analyze the field H mu nu. Well, let me leave it like that. Now, this field has an equation of motion. So the equation of motion, just like the first equation there for the photon, this one has an equation of motion. It would be p squared H mu nu minus p alpha p mu H nu alpha plus p nu H mu alpha plus p mu H, where H, this is 0, where H is H mu nu eta mu nu. So that's a complicated equation of motion, and it has a gauge invariance. Just like the photon equation, and it's delta H mu nu is equal to I p mu epsilon nu plus I'll put the I in front, I p mu epsilon nu plus p nu epsilon mu. Okay. So first thing to notice, in the case of electromagnetism, the gauge parameter had no index. In the case of gravity, it has an index because it has to do with diffeomorphisms, reparameterizations of space and time. So you are really, these epsilons have to do with transformations of coordinates, changes of coordinates, reparameterization invariance. It's not too hard to show that this thing leaves this equation invariant. But now you have a more complicated gauge transformation, and what fields are you going to have? You're going to have that H mu nu contains Hij, H minus I, H minus minus, things without the plus, that's all it has. Then it contains H plus I, H plus minus, and H plus plus. These are all the fields in light coordinates for a graviton. And you have an epsilon for gauge transformations, an epsilon mu. Well, what does an epsilon mu contain? An epsilon mu contains an epsilon I, an epsilon minus, and an epsilon plus. What is the light gauge condition? The light gauge condition is that any field that has a plus can be set equal to 0. So all this identically 0. This is light gauge condition. And the way you do it is by showing that the gauge transformation allows you to do that. For example, delta of H plus plus would have a P plus E plus. So you can use E plus to gauge away this one. Then E minus to gauge away that one, and EI, the collection of EIs, to gauge away all of this. So I'm not doing it now on the blackboard slowly, but please read it. It's sort of clear that this, you have right enough. Here's one thing, so one thing. One thing with one thing, you use it. Oops. Wow. I would have wanted to know how to do that. Unbelievable. Let's see. Where is it? It all went, wow, that's amazing. Let's see, the front, should we move them a little or it's not worth it? Yeah, I want to say a couple more things there. So the rear should go all the way down. And the front all the way up. In the middle. Okay. So this is the light gauge condition. And then these two must be solved for. The things with minuses are always solved for. So you must show that from this equation you can solve those components. And then everything is solved in terms of Hij. Let me show you one little unusual thing that happens with a graviton. If you take the equation of motion and put index mu equal nu equal plus, well, H plus plus has been set to 0. Here there's one plus, so it will be 0. Mu is a plus, so this will be 0, and only you have this. So actually, P plus P, the equation has become P plus times H is equal to 0. So H, which is H mu nu eta mu nu, is equal to 0. So what is this thing? This is minus 2H plus minus plus HII equals 0. Remember, you sum plus, minus, minus, plus. And therefore, actually, there is a constraint here. because h plus minus is already 0. So you get HII is equal to 0. So this says that these HIJs are almost independent, but they must have 0 trace. This is summed over I, as always. Every repeated index is summed. So Hij is symmetric, traceless, and d of size d minus 2 times d minus 2. Each index I and j is d minus 2. So you have the number of degrees of freedom is a symmetric, traceless, d minus 2 times d minus 2 matrix. So how much is that? Well, this is 1/2 d minus 2 times d minus 1. That's the size of a symmetric d minus 2 times d minus 2 matrix, minus the trace is 1. That gives you the formula 1/2 d times d minus 3 is the number of degrees of freedom of gravity in any number of dimensions. So in 3 dimensions, there's no propagating degrees of freedom. In 4 dimensions, you have 4. This is 2 times 1 is in d equal 4. N is equal to 2. In d equal 5, I have it here is 5. In d equals 10 is 35. 35 degrees of freedom for a graviton in 10 dimensions. And in d equal 26, you have 299. Finally, graviton states, well, apart from the tracelessness condition, you would write the following. You would write creation operators, say one graviton state. You would have creation operators always specified by P plus and P transverse. You would be acting on a vacuum. But this time, the fields, at the end of the day, all these fields, the equation of motion for these fields is a massless field equation. By the time you're all done, the equation of motion for these things is just p squared on Hij is equal to 0. So they're all like massless degrees of freedom. So just like scalars, so you must have the indices Ij here. So maybe I should write it like that. Ij, this is the operator, and this is all daggered. And this would be a one graviton state. You would have to put a polarization vector here just like that if you wish to construct more general states and sum over I and j. But the condition that this, in the classical field equation, that this is traceless, means that the states have to satisfy a similar condition, and this psi I must be 0. That's the story for gravitons. The trace of this polarization matrix should be 0. So this is basically the reason I've done all of that is because when we'll quantize the string, all these states will show up in a somewhat different guise, but you really have to keep in mind the key results. And the key results at the end of the day are this one, and the one there. Those are the key things. And the ideas that there's a number of degrees of freedom that for the graviton is this one, symmetric traceless matrix. For this one is d minus 2 degrees of freedom for a vector field. And for that one is 1 degree of freedom. Okay, so yes?
So what is the relation between this degree of freedom and the possible helicity state? Because massless particles only have two Halley-Speed states in any dimension?
Not in any dimension, in 4 dimensions. In 10 dimensions, a massless graviton has 35 degrees of freedom.
That's also the Halley-Speed state?
Well, helicity is a concept that is quite nice in 4 dimensions. It's not that simple. It's not like a U1 symmetry anymore. You know, when you fix a direction in space, you can do rotations only, a U1, so you can classify by helicity. But once you fix a direction in higher dimensions, you can do more things. So that's very important. The graviton, you know, this thing that all these massless particles have 2 degrees of freedom and things like that, it's not true anymore once you go up. And this analysis is basically what it's telling you. The set of states are the number of possible polarizations. This is supposed to be symmetric, runs over d minus 2 times d minus 2 values, and is traceless. In 4 dimensions, if you have d minus 2 times d minus 2, and you're symmetric, well, this number is equal to this one. And if this is traceless, let me put BB, and if this is traceless, it's A minus A, and you have 2 degrees of freedom. But you go up, you have a lot more. Okay, so now let's do the quantum particle. Let's see how we do. So point particle quantization. Particle quantization. So we had an action for the point particle that was minus m, integral from initial tau to final tau of minus eta mu nu x dot mu x dot nu. And now we identify, therefore, I'm sorry, there's d tau here. Let's think of tau as if it would be the time. So think of this as integral d tau of a Lagrangian of tau. I'm sorry, L of tau. So L here would be minus m, and I'll just write minus x dot squared. That's what it is. If you want to do the canonical quantization, you say, what is the momentum? P mu is dl dx dot mu. Well, we take this derivative, and this is minus m times 1/2 this, I'm sorry, this minus x dot squared. I'm sorry. Minus x dot squared. And then I have minus 2 times x dot mu. I'm sorry, here I should put x mu up. P mu with index down comes with this derivative x mu up. And then if I take the derivative, I get the square root minus 2 times x mu down here. So I cancel all these factors, and I got m x mu dot over square root of minus x dot squared. Now, the usual thing that you do when you are quantizing is you say, OK, now let me calculate the velocities in terms of the momenta. But that is not easy this time. In fact, it can't be done. Well, you could say, look at that equation. How do I know that I cannot solve for x mu in terms of p? I claim you can't. You can try, but you won't succeed. There's one way to see you won't succeed. Suppose you found the formula for x mu in terms of p. Well, if you change that to 2 times that, this thing remains the same, because there's a factor of 2 here, 2 squared, 2 So this is ambiguous. There's no way you can solve it. There cannot be a given formula for x in terms of p. So this requires fixing of the gauge, fixing of reparametrization, doing something. There's another peculiarity of the covariant quantization. Even though you can't solve for x in terms of p, you can try to write the Hamiltonian that would be this thing minus the Lagrangian. Well, that you can do because you have the formula for p in terms of x dots, and you put it here. Now, of course, this should be left at the end in terms of p's only, but, well, forget about that. You substitute what p is and x dot, and you calculate this, and out comes 0. It's a very disturbing fact, but the Hamiltonian vanishes. And therefore, the covariant quantization of this thing is subtle. You have to think what's going on, and we don't try to do it this way now. We'll do it that way later. So we're going to do it in the light cone. So from here, I want you to notice that p mu times p mu is equal to minus m squared. And then I'll have this formula here, p mu equal m x mu dot over square root of minus x dot squared. I'll call it formula 1. And this is the constraint. And I will put a light cone condition. Similar to what we've been doing so far, we want to put x plus something with p plus tau here. For units, I'll put 1 over m squared here, because tau will have no units. And therefore, I want this to have units of length. This is x plus, not x dagger. No. And p has units of mass times velocity that has no units. And therefore, this has 1 over mass, which is equal to length. And this is fine. So once you put this, you can go to equation 1 and see what happens for the index plus. P plus would be m x plus, I'm sorry, this mu index should be on the right position here as well. P x plus dot over square root of minus x dot squared. Now what is x plus dot is p plus over m squared. So 1 over m square root of minus x dot p plus. So from this equation, you see that imposing the light cone gauge, and given the definition of your momenta, you've learned that this p plus and p plus cancel. So m times square root of minus x dot squared is equal to 1. And that simplifies the equation of the momenta, because now using this, the momenta p mu over here is just m squared x mu dot. Using that last equation over there. So, or x mu dot is equal to 1 over m squared p mu. Okay, then what happens? We're basically in shape here. Let's look at this equation. This equation for mu equal plus should work correctly. If mu is equal to plus, indeed, you take the dot of this equation and it's consistent. We did it this way. So this has information for minus and I components. So it says that dx minus d tau is equal to p minus over m squared. Now, what is p minus? You can calculate p minus from this equation. As usual, p squared equals to minus m squared, or p squared plus m squared equals 0, gives you p minus 1 over 2p plus pi plus m squared. So that's what p minus is. So p minus is known, m squared here. So x minus of tau, the solution, is x0 minus plus p0 minus tau over m squared. That's the solution of this differential equation with an initial condition x0 minus and p minus, no, p0 minus, p minus, given by that formula. For xi, you would have dxi d tau equal pi over m squared. So xi of tau would be x0i plus pi tau over m squared. And that's it. You've solved everything. This system has been totally characterized. The equations of motion have been solved, and we use the light cone. So what we want to extract here is what we need to pass to the quantum theory. And what we need is a list of dynamical variables, or constants, or things that will determine all the physics. So what do we have? Well, we have for the particle the value of p plus is necessary to determine the physics. P plus in here. Then we need the values of pi. We don't need the values of p minus. Those are physically determined. So these are quantities that must be stated. We will say, therefore, to get x minus, you need x0i. And to get the rest of the dynamical variables, we'll say, OK, you could put here x0i. That's the last one that, I'm sorry, no. I wanted to say here x0 minus. To get x minus completely determined. And here I could put x0i. But I will rather, for similarity with this pi, I could say, well, I know this term. Either my dynamical variable can be called this or this, and I will work with just this one. Xi will be better for us. So these are going to be our dynamical variables, and we're going to try to make a quantum theory out of this. So a light quantum theory. So basically, in mechanics, you have a p and an x, and you turn them into operators, your Schrödinger operators. So we're going to do the same thing. We're going to state that our quantum theory has Schrödinger operators that are going to be xi, this list basically, x0 minus, pi, and p plus. In a sense, we're now trying to invent the quantum theory. I think you should be aware that inventing a quantum theory is a work of art. You can't just follow a recipe. There's no great recipes for inventing quantum theory. Yet people say, well, if you have a first-class constraint, do this and that and that. But most of the times you find yourselves that things are very complicated. You just have to feel your way through. So let's feel our way through. We're going to start with these Schrödinger operators, and we need to state commutation relations. Now, it's natural to state that xi with pi, pj, will be I delta ij. Seems pretty reasonable. And then that x0 minus with p plus would be sort of I eta plus minus. Is that right? That's naturally what you would imagine should be. So this probably should be taken to be equal to minus I, and all others 0. Others 0. I'm running out of time. I'm going to use 3 more minutes and leave it there. So you've defined some Schrödinger operators. Now, there are some Schrödinger operators that are defined by including time. Time-dependent Hamiltonians can be defined. So what are other Schrödinger operators? You can define x plus of tau is a Schrödinger operator, but just means this, p plus tau over m squared. That's reasonable from your Leibniz gauge condition. So this is an operator, and these are numbers, and this is a definition of another operator. You can define x minus of tau to be x0 minus plus p minus tau over m squared. And it's also time dependent. Here there are 2 operators, this operator and there's tau. And these are just definitions. And there's finally the p minus that you can define, which would be 1 over 2p plus pi plus m squared. Last thing I want to say is some remark about Heisenberg operators. Well, one other remark. Suppose you want to calculate, this is sort of funny, x plus with p minus. How much should that be? There's 2 ways to think about this. First, intuition. And you know, everybody's intuition, I think, is this one, that x mu with p nu is somehow equal to I eta mu nu. Reasonably looking equation, but it's a very strange one, of course. Certainly for spatial ones, this is true. Well, maybe it's true more generally, but we usually don't think of x0 as an operator. So anyway, but if this is true, this is sort of the logic that led us to this minus I, because x minus with p plus would be I eta minus plus will be minus I. So you would say, okay, so x plus with p minus should be the same, minus I. But that's not true. Why? Because these operators, indeed in the LightCon, the 0 operator is not intrinsic. It has been defined, and it's this. So this operator was not in the list of your Schrödinger operators. It was created by a definition, so you must use the definition to calculate it. So this is p plus tau over m squared. And here is p minus. That was also not defined as the list of Schrödinger operators that the theory has, but it's a new definition. So you have 1 over 2p plus pi plus m squared. And what is this commutator? Well, this is the only operator. It commutes with p plus, certainly. It commutes with pi, because we said all others are 0. And therefore, this commutator is 0 in this theory. And that can worry you, and it would be a reasonable thing to be worried, because somehow this naive logic has led to trouble. But that's why the Leibniz gauge is very non-trivial. you have to beware what are your basic operators and what are your derived operators. So the thing that we'll have to do next, but that will be next time, is to consider the Heisenberg operators. And what are the Heisenberg operators? Well, the Heisenberg operators are defined from the Schrödinger ones if you know the Hamiltonian. In this case, we don't know the Hamiltonian. We're going to have to guess it. But the Heisenberg operators are Schrödinger operators with time dependence. So they will be this thing, pi of tau, and p plus of tau. And again, I think you would be justified to be a little concerned because the xi's, yes, Heisenberg operators are the analog of time-dependent variables in classical mechanics. So xi will have a time dependence. And pi, probably not, because that was conserved in the theory. The momentum is conserved for a free particle. P plus shouldn't have a time dependence. And x0 minus, no, it's a constant of integration, shouldn't have a time dependence. So whether they have a time dependence or not depends on the Hamiltonian. And we have to invent the Hamiltonian. So it may be a good place to stop now, because in a sense the puzzle is completely set up here. You're trying to invent a quantum theory that resembles the classical theory. You define some Schrödinger operators, and you define some commutators, and so far, things are fine. But now the catch comes. You must have Heisenberg operators, and you must invent a Hamiltonian. And in such a way that the Heisenberg equations of motion of these operators correspond to the classical equations of motion of the field theory. That is the Heisenberg idea in quantum mechanics, that as operator equations, the Heisenberg operators evolve as the classical dynamics does. So we understand the classical dynamics. Our task is to invent the quantum dynamics. Exactly what we will do in next lecture, when we'll do for the strain as well. All right, we'll stop here.